it's our great pleasure to have Professor Fred Mannering to be our plenary session speaker. I believe a lot of you know him. At least when I consider where to go for my postdoc, I actually was attracted to the University of Washington because of Professor Mannering. He was our department chair at Civil and Environmental Engineering here, and he was also school head at Purdue University. He's currently executive director for the Center for Urban Transportation at University of South Florida. And Fred has a lot of honors. Maybe you read his paper before. He has the Google Scholar citation over 35,000. Is one of the most cited scholars in the world in transportation area. Now let's welcome Professor Mannering.
Thank you so much. It's good to be back at the University of Washington. I think it's been like 17 years since I've been back on campus. So I've been visiting, some friends. It's good to get caught up. So what I'm going to talk about today is sort of the interface between artificial intelligence and machine learning and traditional statistics and econometrics with applications to safety. So when we think of artificial intelligence, sort of fundamentally, it aims to mimic the problem-solving and decision-making capabilities of the human mind. But given some of the people that we've elected in politics, it's hard to imagine this is necessarily a good goal. So, given the weaknesses of the human problem-solving and decision-making, this is potentially problematic goal. But now I've put some sort of, if you go online, you can find multiple things that have these different AI levels. One is, the scripted intelligence, sort of like calculator, reactive AI is Roomba, limited memory AI is sort of autonomous vehicles. Then you have context-aware AI, and then theory of the mind. Now, there are levels above this where AI becomes aware of its existence and everything else, but we're not going to get into those philosophical elements. But we're going to see how far we can go with these 5 levels. If we look at AI ML applications in the safety area, there's a couple things to think about, and I'm going to go into details in subsequent slides, but there's the data size and its complexities. There's the richness of the data. A lot of times we have a lot of data, but it's not really high quality data. So there's a richness. I think one of the members on my dissertation committee won the Nobel Prize in Economics, Dan McFadden. He calls this the data desert. There's a lot of data, but it's not like a database you would get if you were specifically targeting something or someone with a survey. Then there's the unpredictable elements of human behavior. There's the human-machine interface, which I'm going to talk about. There's underlying causality. A lot of times we focus on prediction without understanding what's actually happening, and I'll talk about this. And then there's this notion of temporally shifting behavior, is that people's behavior is constantly changing and adapting to the technology around them. So when we look at AI applications in safety, I'll give you some brief sort of categories. There's obvious applications, there's applications that would merit some caution, and then there's applications that merit extreme caution. So the obvious applications, you would have video analytics where you're collecting data in real time, the interpretation of sensor data, vehicle and infrastructure, connected and autonomous vehicles. You're just processing sort of physical data like elements related to Newtonian physics, friction, so on. Real-time data processing. These are things that happen so quickly you don't have to give much thought to what is happening in terms of underlying causality. The applications that merit some caution is when you get to naturalistic driving data. So here you're collecting a lot of data from sensors, but you also have human elements involved. Driving simulation data, again, you're having humans involved. So really, large data that involves human decision makings, you have to be cautious about AI, MI applications. predicting trajectories becomes, it's easy to be able to plot out the trajectories using video analytics, but when you start predicting what the trajectory is going to be, then that becomes problematic, especially if you have a human driving the car. So anything with human input would merit some caution. Then there's the extreme caution, is when you have what we call traditional small data, like a crash data, police reported crash data. Applying the machine learning to that is like overkill. And again, I'll talk about details. But there's data analysis that's seeking to understand human behavior, data that's afflicted by unobserved heterogeneity, because you collect a lot of data, but there's also things that you don't fully understand. So there's always going to be something that you don't collect. And then there's going to be data that's involved temporally shifting decision making. And again, I'm going to talk a little bit more about that. If we look at the data analysis methods, economists and experimental economists use what they call causal inference models. And what these, and I mention this because for many years, I work in econometrics. For many years, we would say, oh, these people use these simple causal inference models because they don't understand the mathematics of more complex models. But since they actually won a Nobel Prize in this last year, so now I have to pay them some respect. So causal inference models, what they do in those models, and again, we don't use these in transportation very often, but they aggregate the data to try to isolate a specific element of the problem. So again, we don't use these, but I put this in because it's one of the potential data analytic methods. For us in safety, there's the traditional statistical models, the heterogeneity models, which are random parameters models, so we put in mixing distributions to account for unobserved heterogeneity. And then there's the data-driven methods, which are the AI ML models. So when we look at the data-driven methods that have been applied to the analysis of safety data, support vector machine, random forest, there's artificial neural networks, all of these you've probably heard in your courses and stuff. So all of these have been applied to some extent to analyze transportation and specifically highway safety data. But when we think more fundamentally about these 4 different types of data analytics we can bring to the table, we can think of data size and the prediction causality trade-off. And so I came up with this really cool diagram. Now I should tell you, this is the 3rd time I've given this talk. I started my career at Penn State in 1983. So I gave this talk in September, and then I gave it at Purdue later in September, and I'm giving it here. So I told my daughter, I'm giving this talk at these universities, and one of my daughters said, Dad, you should have T-shirts made up with your tour, your 40th anniversary tour. And so I did have T-shirts made up. This is what's on the front of the T-shirt. If you want to buy them, they'll be merchandising after the talk. So the front of the T-shirt has this on it. That's why I read. And then on the back it has 40th anniversary tour, Penn State, Purdue, Washington, and then Saudi Arabia. I'm giving this talk in Saudi Arabia in August, in December. Providing things settle down in the Middle East. But here's the idea with this, and this is something to think about. If you look at predictive capability, data-driven methods, AI, ML, will always predict better. So, when I have papers submitted to the journal I edit, Analytic Methods in Accident Research, they say, oh, look, machine learning predicts better than the statistical model. That's obvious. It has to predict better because they are designed to predict. What they're not designed to do is uncover causality, right? So you have this other element of this triangle, this causal inference capability, and that's where AI and ML is weak. Currently it's weak, but potentially that could be improved. When you look at AI, ML applications, incredible big data suitability, right? You get all sorts of excellent predictive capability, but not so good with the causal inference. And if you look at this little gray triangle, the traditional statistical methods, there's a yellow triangle that completely surrounds that. And that yellow triangles are the heterogeneity models. So those are the ones where we introduce, again, econometric models where you introduce mixing distributions. They fit the data better, and they can uncover more causality. The one little I guess it's a sort of a dark yellow, reddish, the causal inference models, have virtually no, bad on prediction, bad on big data, but they can uncover a specific causality. And again, those are used primarily in economics, not so much in transportation. But if you look at the two best methods here, which would be the AI, ML, and then also the heterogeneity models, you could see if you could somehow combine those, you would get something like this, where you would be able to get good prediction, have big data suitability, but also uncover causality. So let's talk about some key analytic considerations. Now, economists and statisticians have spent many years sort of understanding what's going on data to understand behavior. So the things that they've addressed are unobserved heterogeneity, which are things that you don't observe. Observed heterogeneity would be like the age and so on. Selectivity, endogeneity, and identification. I'll give some examples of that. The temporally shifting behavior, and then compensating behavior. So let's look at first at unobserved heterogeneity. Data collection for any analysis, any data you collect, it's never quite complete. So if you're doing video data at an intersection, it would be great if you could do facial recognition to determine who the pedestrian was. Then you could link it to their age, because then you could predict their trajectories much better if you knew the age of the pedestrian and so on. The statistical analysis methods have been developed to handle this. In these methods, we assume that this unobserved data has some distribution. But when you think of AI, ML applications, a lot of times they overlook. So for example, you could have an ML algorithm that uses a logistic regression as part of the algorithm. So you could use like a mixed logit model or a random parameters logit model, and you'd be able to have a better ML algorithm. So if you do not account for this unobserved heterogeneity, then you get inaccurate predictions and erroneous inferences and conclusions. Now let's talk about it, because I have a couple examples here. Selectivity, endogeneity, and identification. These are elements that we have conveniently ignored in the safety profession. So safety data is often afflicted with a selection process. And as an example is crash data. When you observe people in a crash, you only observe the riskiest drivers, right? Because they're the ones getting in the crash. So you have a self-selected sample. Ideally, you would set up an experiment where you had different people run into a brick wall and then get information. Could you run into that brick wall at 30 miles an hour? This is a joke, by the way. But obviously, we can't set up an experiment like that. So to compensate for that, we're going to have to come up with some sort of statistical correction, because we do not observe really safe drivers getting into a crash. And you could also think about this as drivers on observed routes tend to be self-selected. So this happens, sometimes you make a safety improvement and then another intersection suddenly gets a lot of crashes. It's sort of like a whack-a-mole with the safety. And what's going on is that there's a dangerous intersection, so the safest drivers avoid that intersection. Then you improve the safety, so then the safe drivers start going to that intersection, but then it's too congested. So the risky drivers that were causing crashes at that intersection go to another intersection, and so suddenly you get an increase of crashes at another intersection. So that's sort of the logic with that. Now, the consequences of the self-selected data is you get biased safety predictions and you're unable to understand what is going on. So you're unable to identify causality. So let me give you an example of a motorcycle safety, because we were talking about motorcycles. So in motorcycles, we often estimate a motorcyclist injury severity model that shows we have a rain indicator. One of it is raining, zero of it is not. So we find that rain indicator increases the severity of the crash. But there's two possible explanations for that. One is the rain actually does increase the severity of the crash due to reduced coefficient of friction, all the physics involved. But the other one is that the people that ride in the rain are only the riskiest riders. So maybe the rain has no effect on the crash. It's just that now you're observing the riskiest riders and they're going to have more severe crashes, whether it's raining or not. Usually it's a combination of those two, but uncovering what is the physical effect, the physics involved, and what is the self-selectivity effect can be difficult. So the other one we have, and this is a paper I wrote in the early 2000s, is when you look at safety features in cars. And I remember this explicitly because I was on a Good Morning America interview with the research results. Side impact airbags. So you reduce fatalities relative to now if you put a new safety feature in the car, the easiest way to estimate their effectiveness is you look at the drivers with the side impact airbags and the drivers without. And you find that the drivers with the side impact airbags have far less injuries. But there's a self-selectivity going on there because side impact airbags are the people that buy safety features in cars first are the safest drivers. So you're always going to overestimate the effectiveness of the safety feature because you're in the safest drivers buy the safest vehicles. And you do not know the full effect of the safety feature until everybody has one, right? And with the side impact airbags, they originally started in 2004, I think they were 45% effective in reducing fatalities on side impact airbag collisions. Then it became 35, 28, 22. Eventually, because now the risky drivers are starting to use those cars. You don't know the full effectiveness until you get it through the whole vehicle fleet. Now in statistics and econometrics, there's James Heckman, who won the Nobel Prize in Economics in 2000. He developed a correction for this, but on a very simplistic model. It was a binary logit model with a regression. So the models that we use in highway safety are much more complex than this, and it's very difficult to apply a Heckman-style correction to that. But this sort of self-selectivity problem has been largely ignored. It's been ignored in the statistics and econometrics, but certainly in AI, ML also. Now, a lot of these problems exist no matter what method you're using, but you have to understand what's going on to be able to interpret the results correctly. So then there's this idea of temporally shifting behavior. You know, the idea here is that human behavior is constantly shifting. There's behavioral shifts can be induced by technological changes, changes in risk perceptions, changes in societal norms. I remember I sometimes have a paper submitted to my journal that will use data from 2002 to 2022. Imagine how you drove a car in 2002. I mean, you didn't have an iPhone, you didn't have Apple CarPlay, you didn't have any. It's so much different. There's no way that you can put that many years of data together and expect the behavior to be the same. And there's ample evidence in safety and travel behavior literature that shows that the model parameters change significantly over time. So ignoring these temporal shifts in parameters can lead to erroneous inferences and predictions. Next is the compensating behavior. And you can think about how you drive and sort of think about this compensating idea. The idea then, if you introduce a safety feature in a car, people will say, this car's a lot safer now, so I can drive faster. The expectation we have as engineers and transportation professionals is that we introduce a safety feature in the car, those benefits are going to be extracted in improved safety. So let's consider a technological innovation that improves safety. So we have some initial conditions. You have these nice little curves here. There's going to be uncertainty about these probability curves. But on the x-axis, I have the normal, what you would consider safe driving speed. On the y-axis, we have the probability of a crash. So we have these initial conditions. You have an equilibrium point at point A. So you might say, I like to have a 1 in 10,000 chance of having a crash. That's what I consider to be an acceptable risk. And every person will have a different value. So let's say we put in a safety innovation that shifts this curve downwards. So the expectation we always make as transportation professionals is we'll go to point B, that people will keep driving the same and we'll just this will be a significant improvement in safety. But realistically, there are some, at an extreme case, if I like to have a 1 in 10,000 chance of having a crash and you make it a 1 in 40,000 chance, I'm going to drive faster or drive distracted, right? It's easy to drive now, so I can start texting. So you could end up at point C where you get no benefit. Now, there's still benefit to society because you're able to drive faster or you'll be able to text along the way. But so there's this compensating behavior you have to think about when you put in any sort of safety feature. So if you ignore this compensating behavior, this can lead to an overestimation of the safety innovation effectiveness. And this has happened in so many safety innovations. We say, oh, the side impact airbags are going to be 45%. By the time you do the compensating behavior and the self-selectivity, it's much less than that. So these unexpected consequences you can expect. So just think about the possibility of compensating behavior. So what do these sort of elements that the statistics and econometric fields have struggled with for years, what do they say? Well, they say you really have to think about what's going on in the project before you recklessly apply, some method. And this happens in econometrics too. There are people that apply these heterogeneity models, random parameters with heterogeneity in the means and the variance, like incredible complex probability distributions, but they have no idea what's going on in the underlying process. So something to think about is not recognizing the safety complexities and underlying causal effects can be highly problematic. You have to think about what you're actually doing before you start applying the analytic methods. So this is particularly problematic with non-real-time data where you're trying to understand what's happening. So you have to think causality and not just correlation. So when we look at what is the promise of AI ML to sort of address these problems, I'll give an example of the adverse effects of weather. So there would be a human response and an autonomous vehicle response. So when the human, sort of getting back to one of my curves here, if you have normal weather conditions, the human is at point A doing his or her 1 in 10,000 chance of having a crash. Now adverse weather happens. So this is going to shift the curve up, making it more likely that you would have a crash. So if the human keeps going at the same speed, they'll move up to point B and they'll have a higher probability of a crash. So it starts raining or snowing. I guess I could use snow here. I can't use the snow example in Florida because I'd say, whoa, what's that? But you would ideally like the person to go to point C, right? So they predict what the coefficient of friction is, they slow down appropriately and keep their 1 in 10,000 chance or whatever. Now, when we look at autonomous vehicles, we sort of have the same curve, but with autonomous vehicles, potentially we could get a near certain prediction of those probability curves. Because we would have sensors that are picking up the coefficient of friction on the road and so on. And these curves would be lower because you don't have to worry about reaction time and stuff because you have an autonomous vehicle. And we could ensure that you get to point C. So if the autonomous vehicle is designed to have 1 in a million chance of having a crash, you could adjust the sensors and the speed and everything to get to that point. So you can sort of envision, well, what could you do with this? So you could think of something like an AI-assisted driver where it correctly calculates these probability curves that I just threw up, and it adjusts the systems after learning driver responses. So this is sort of one of my ideas for this talk, and something that students should think about, is think about how your AI ML can train humans, how it interacts with humans. Because this is the part I think that we're sort of ignoring so far in the development of autonomous vehicles. So you could imagine if you had an AI-assisted driving, you notice this person is starting to drive more recklessly because they have a really good braking system. Then you could design the AI system to make the driver believe that the braking system's not as good as it actually is, so that they don't do that risk compensation. Because the risk compensation is what they're doing, is they're not improving the safety, but they're being able to drive faster or text. So you can mitigate these risk compensating behaviors. So what role will AI ML play in improving safety? We have to be a little careful because current issues with a lot of AI ML applications in safety is being applied without much thought or understanding of these sort of higher level concepts of endogeneity, self-selectivity, and so on. And you can think of it, and I can't blame you, students get a new way of analyzing data, and it's sort of like a hammer in search of a nail, right? You're just looking, oh, I'll apply AI ML to this. You still have to think about what's fundamentally going on. So ML is justified, and the other thing is justifying ML on superior predictions is not good, because it is always going to predict better. Statistical and econometric models are not just designed for predicting, they're designed to understand what's happening. So those are the elements that we have to bring, I think, into AI ML. So AI ML for safety data applications, we've currently been thinking about it as a new way to solve old problems. But we have to think it should be used as a tool to explore problems we have conveniently overlooked, like the selectivity bias. Those are things we know exist, but we don't, we sort of overlooked them. Or it can be used to study problems that have not yet been imagined. So I'm going to imagine some of those problems now. So for the overlooked ones, we can talk about the selectivity in data that I talked about. If you get crash data, it's a self-selected sample of risky drivers. Safe drivers don't get in crashes, so they're not in your crash database. Temporally shifting behavior and compensating behavior I talked about. Things that have not yet imagined would be mitigating dangerous human behavior by managing the machine-human interface, and using autonomous vehicles to alter the behavior of human-driven drivers around them. So and then some things you can. So here's the current approach when we think about how we're designing autonomous vehicles. We're designing them to avoid collisions in response to human-driven trajectories, right? So that's really but an alternative approach would be to design autonomous vehicles to interact with human-driven vehicles to alter crash-critical vehicle trajectories before they happen. So, flashing brake lights, weaving erratically. Because here's what's going to happen when you start introducing autonomous vehicles into the vehicle fleet. They're going to be much more predictable than humans, right? So human driving behavior is going to change significantly around the autonomous vehicle. You'll be able to tailgate an autonomous vehicle without getting shot, and things like this, right? You're going to change your behavior, but the habits you get into around autonomous vehicles is going to affect how you interact with other human-to-human vehicles. So if we don't think about how autonomous vehicles are going to change the human driving behavior, we're going to see a lot more human-to-human crashes when we start introducing autonomous vehicles. And, I have a little case in point. I have a friend in California. When he's behind an autonomous vehicle, I can't remember what model it is, but he's determined that he's found out that if you start beeping your horn, it's programmed to pull over. So he's going 35 miles an hour, right? It's going the speed limit. He wants to go 45 miles an hour on a two-lane. So he starts beeping his horn, the car pulls over, and then he just drives by it. So it's going to be amazing how humans start changing their behavior around autonomous vehicles. And the problem with that is that changes in behavior around autonomous vehicles are going to also be changing around other human vehicles. So when you think of the future AI, ML, and safety, we need to integrate data-driven analytics with the causal principles of econometrics, because econometricians and statisticians have studied this causality for decades. But suddenly, we're jumping in with AI, ML, and we're sort of ignoring this selectivity, all of these things that have been known to be behavioral problems. And then draw from the fundamentals of cognitive science to interact with AI, ML, and the AI, ML human interaction. Now, as a final point, I noticed that my daughter is actually a cognitive scientist, and she's working now for the Applied Physics Lab at Johns Hopkins. And she's working with, supplying AI information to fighter jet pilots, and then also having the next generation of air dominance fighters control multiple drones, have AI control of multiple drones. But the problems that she's addressing are really the same problems that we're going to have with autonomous vehicles. I mean, it's on a little different scale because, a driver's not going to be like a fighter jet pilot. A fighter jet pilot, extremely well trained, but they don't have much cognitive bandwidth left because they're, dodging missiles and stuff like that. Human drivers are going to be texting, and so you don't have as much. There's a lot of potential cognitive bandwidth there, but there's bad training and a lot of bad behaviors. But what we can see is that there's a great potential to introduce the cognitive and behavioral sciences into AI, ML applications. And so I think that's part of the final, point that I wanted to bring up. I think it's, AI, ML applications are going to be, it's a groundswell that's coming. But we have to keep in mind what we've learned from decades of statistics and econometrics, because those same fundamental data analytic problems just don't go away because we're applying a new method. Thank you. Yeah.